We are going to do lesson 3 this week, I think. If you haven't already given me your Penn State email, if you can go ahead and put that in the chat box, that would be awesome. So listen, I was gonna go to the game. That was the plan. But I also dog sit, and they said, Anne-Marie, would you like to dog sit on Saturday? I was like, yes, I would. And then I thought about it. I said, isn't Saturday the... So I'll be watching it on the television with some doges around me. So yeah, unfortunately I can't. I know. I wish I was going to the game, but sad I cannot go. But yeah, I'll definitely be watching it on TV. It should be good. I'm excited. So I hope it's fun. But I hope you guys get to watch it or go to it or whatever. You guys are probably far though. But yeah, I'm definitely gonna tailgate. I'm looking for some buffalo chicken dip, you know what I'm saying? So I'm trying to like get me some of that. Really. So I'm definitely gonna tailgate for in the morning, I guess. But oh, you're in State College. Okay, cool. Then you get to go. All right. Yeah, I know some people are like all across the country, but but yeah, I wish that I could go. I hope you get to go, Tammy, or you get to watch it or something, or tailgate. All the above. But but yeah. All right, cool. I hope you guys had a good week so far. Oh, okay, cool. All right, I'm glad you get to go. You'll have to tell me about how it was on Sunday then, because I'll have to live vicariously through you. So sad. A Penn State student, I'm not even going to the game. I'm ashamed of myself. But yeah, okay, so like I said, we're going to do lesson 3 today. Continuation of last week, we're still talking about describing data, but we're just going to go into some more, a little more in depth, some different parts of it. Okay, so let's talk about this. I just want to go over Boxplots. I know I keep talking about this, but it is important to remember because these are very useful. I think when you have a 5-number sum or anything like that, they're very useful. So I would just make sure that you're able to like label all the parts of a boxplot. So like, just if you're bored, if you're feeling fun, go ahead and label a boxplot. This is what I do in my free time. I just draw me up a boxplot and start labeling it, so you guys can too. So you know, you have your minimum, your max, and then remember down here you got your Q1, your Q2, and then your Q3. Okay, and what pop quiz, what is the Q2 always? Like, what is this black line in the middle representing? Yes, snaps. I thought I couldn't snap anymore, but I can. I feel like the other day I couldn't, but we good. Good job. Absolutely. So yeah, Q2 is always going to be our median. And don't forget that percentiles come into play here too, because we're talking about quartiles. So that means that we have like these 25 things going on like quarters. So this is our 25th percentile, our 50th, and then our 75th. So another pop quiz. I'm gonna start doing this. I'm gonna start just like throwing stuff in here. Okay, what is that not helpful? I feel like it might be more helpful than me like talking the whole time. I always feel like I'm talking so much and I'm like, they're probably so bored and they just want to go to bed and I just keep talking. But so maybe we spice it up a little with some questions. I don't know. Maybe I would hate if my professor did that, but I don't know. But low-key pop quiz. At what quartile or at what point in this on a box plot does 75% of the data lie at or below? So at what point on the box plot does 75% of the data lie at or below it? Yes. No question marks. We want exclamation points. You want to be confident in your answer. Yes, I know you're trying. That's what I'm saying. Yes, that's right. Q3, Q3. Good job. Awesome. Oh, P.S. I realized I need to start, remind me, I need to start repeating questions that you guys ask, because I realized, like, on my recordings, I was gonna say, did I record this? Okay, it's recording. Bless. On my recordings, like, the chat box doesn't pop up, so at plenty of points it just looks like I'm kind of talking to myself, and because I'm answering your questions from the chat box, but no one can see them. So remind me to do that. I want to make sure that everyone knows what's going on if they're watching it back or whatever. But anyway, good job. So yeah, definitely keep in mind a box plot. Remember, we often see this with our 5-number summary. So that's just something to keep in mind. But okay, good job. You guys are doing great. Killing it. This one's not as long as last week, by the way. Last week was pretty rough, I know. That was very long, but this one's not as long. At least I don't think so. I tried not to make that long. But okay, so first thing, I want to talk about the IQR method. So we talked earlier, like last week, about how, like, if you're trying to find an outlier, you can basically just kind of look at that graph and be like, what's that one doing? Why is that all the way over there? Like, that's really suspicious. So then you're kind of like, okay, outlier, like, what's going on? But if you want to actually, like, kind of find, like, objectively where an outlier would be, instead of, because I mean, obviously you can't always just look and be like, oh, okay, that's an outlier. You know, there's certain ways that you can actually find if that value is specifically an outlier, which is where the IQR method comes into play. So what the IQR method does is it creates kind of like a little boundary around Q1 and Q3. So once again, drawing this box plot, like I said. Ooh, this is a nice looking box plot. Oh yes, I'm glad I'm recording this, because this is just wow. Okay, so remember, we have, so let me write out here, we have our Q1 and our Q3. Okay, so IQR method, what it's doing there, all it's doing is creating an area around Q1 and Q3 that if it were to surpass that, then it's going to be an outlier. Okay, so that's like the main idea in this, I guess. So it's creating that area to see, you know, where, like, which one of these would be considered outliers, you know, if it's here, whatever, that kind of thing. So yeah, that's basically all that is, just an objective way to check for outliers. Nothing too snazzy there. Okay. All right. Bubble plots, super cute. Everyone loves bubble. Hi, Isis, how are you? So yeah, everyone loves the bubble plots. I think they're cute. I think they're nice and colorful and stuff. So I'm totally down with them. So basically, these are cool because you're able to kind of put a whole bunch of stuff in one. So you're able to put up to 3 quantitative variables, like, whoa, 3 of them, plus a categorical variable. So, like, it's just, what can't a bubble plot do? Like, this is crazy. It's a jack of all trades. So let's kind of look at this. So remember, quantitative variables are going to be the ones that involve numbers and values on them. So if you want, on a bubble plot, you can have one on the x-axis. So remember, that's this one down here. It's our x-axis. And then one on our y, which is over here, our y-axis. And then a third quantitative variable, so a third variable involving, like, a number, can be the size of the bubble. So, like, you could usually measure it, you know, in diameter. So that can be another quantitative variable if I'm just doing this here, you know, the diameter of it, whatever. And then, as if that wasn't enough, bubble plots say, I can also do a categorical variable. Watch out, world. And then they'd be throwing all these colors on here. And then here are your categorical variables. Boom. Like, that's crazy. Look at all the information you can find out. So that means that I can look at one of these bubbles and I can figure out 3 different quantitative variables about it. So let's just say that this x-axis was, let's say this is cost. Let's say we're talking about, like, a refrigerator. Why did I say that? I don't know why, but we're going to talk about it. So I can't spell it. I'll just say fridge. Okay, so this is going to be a graph about fridges, okay? So this is going to be the cost, is going to be the weight. And then let's say that the size of the bubbles is going to be the height. And then the color is going to be where it came from. Okay, this is just an example. I totally made all this up, okay? So if we're looking at this, I can look at one of these bubbles here, and I'm able to tell how much it costs, what the weight of it is, its height, and then where it came from. 4 different things. So that's 3 quantitative variables, the cost, the weight, and the size, so, or like in the height, and then a quantitative variable where it came from, all from one of these bubbles. So that's what's important about these. They can put a bunch of stuff on one. So I totally made that up. So like you don't know what it is. So like I literally just went like, I mean, I'm just using this as an example. If the x-axis were to be cost, I'm sorry. For those watching back, I was not talking to myself. Isis asked us, how do you know what the cost is? So, and I said that I made it up because the cost is not necessarily, this is just, I'm just saying like you could see what the cost would be if that was on our x-axis and if the y-axis was height. Like this isn't actually true. Yeah, it's just, I just made it up. We need to stop talking about refrigerators. Maybe I'm hungry or something. This always happens during these sessions. I swear to God, I'm always looking for some food. All right, so let's move on from bubble plots. That's enough. That is enough of them. Okay, so time series plot. These ones are cool because they're kind of self-explanatory in the fact that it's always involving time from left to right. So it's always going to be the latest, the farthest away on to the left, and then to the right is going to be the most recent. So our x-axis is always going to be time. So down there you can see the year on the x-axis. That's going to be each year. And then our y-axis will be the quantitative variable that we're talking about. So in this case, we're just kind of looking at the estimated spending over, a time span of whatever this is, 12 years. So this is a good way to kind of see like the trend of something. So you can see the trend of a quantitative variable over time. That's kind of what that comes from. It's not too complicated. So yeah, time series plots are good if you're looking for trends or anything. So, all right. Okay, so these are a few things that we can. These are like graph displays. So we talked about last week, if you remember, we talked about categorical data displays, quantitative, that kind of stuff. But this one is if you want to mix them together. So remember, you can mix them up with the bubble plot that I was just showing you. But this is another way you can do it if you're talking about just one quantitative and one categorical. So for this one, in this case, and we did go over this a little bit, but in this case, we have side-by-side box plots, this first one here. So down here, what is gender? Is gender our categorical or a quantitative variable? Take a guess. Or maybe it's not a guess. Maybe you know. Meow. I'm just kidding. Okay. I'm so annoying. Oh. Yes, so gender is, okay, good. Good job, everyone. Yeah, so definitely. Our gender is going to be our categorical variable because remember, that's going to be the one that is a label. And then, I mean, if you're unsure, you can look at age. And if you know age is going to be quantitative because this has a number attached to it, as you can see on the actual axis, there's numbers. That's going to be our quantitative. So this is just a way that we can compare the two. Same thing with our dot plot over here. Our categorical variable is going to be over here, the supplier, A or B, and then it's also represented here. And then our length is going to be our quantitative variable. So it can be on either axis. It just depends on how it's set up. Oops, I did not mean to do that. All right, cool. I mean, if your dot plot was set up horizontally, it's going to look different. So I know some people try to memorize like categorical will be on the X and Y. Like, don't try to memorize it like that. It's not something to memorize. It's just to be able to recognize which type of variable is which. So, but you guys seem to get that, so that's good. All right, cool. And this is just another example. This is basically the same thing as a dot plot with groups that I just showed you, except this one can be used for larger amounts of data. We have our location is going to be our categorical variable, and then the level of improvement, the frequency of improvement, as they put it, is going to be our quantitative variable there. So that's where that comes from. Alrighty. Okay, so let's talk about scatter plots. This is so scatter plots is a way that we like represent two categorical variables, or sorry, nope, beep boop, two quantitative variables. Control Alt Delete that. Yeah. So we're doing two quantitative variables for scatter plots. Okay, we'll have one on the x, one on the y. So we have our explanatory and our response. So remember, we talked about these. A little, I think it was last week we talked about these. Our explanatory variable is what explains our response. Our explanatory variable is going to be independent, and the response is going to be what, like, it's dependent on whatever happens to the explanatory variable. These four different bullet points I have over on the side, the direction, form, strength, and outliers, those are just four different ways that we use to discuss and describe scatter plots. So if we were to use a specific one as an example, our direction is going to be either positive or negative. And if we're using this one that I have here as an example, I would say that this is in a negative direction because left to right, it's going downwards. So I'd say this is negative. Form, linear, nonlinear. It's kind of self-explanatory. Does it look like a line? Does it not look like a line? I'm saying this looks pretty linear, so we call that linear. Strength would be kind of like how close together are these points? Are they weak, moderate, strong? Are they, super close together? Are they like totally spread out? This one I'd probably classify as like moderately strong. They're pretty close together. They're not in a like straight line or anything, but I'd put it somewhere in here, moderately strong. And then outliers, I don't really see any, but that could be something like if you were to see something over here, like over here, it's like, what you doing over there, buddy? Like, get out of there. So, that's just how you would like use these things to discuss a scatter plot. And remember, that is for two quantitative variables there. All right, cool. All right, so this is basically the same thing I just said. The only difference with this scatter plot is that there's multiple groups. So they're throwing in a categorical variable here. So we still have two quantitative variables on the x and the y. So we have our length and width. So we have our length on our x, our width on the y-axis. And then you have the scatter plot. You have all the different points there, but the different colors. Technically, I mean, it's a different color and a shape for each of them. But basically, the different points, as you can see, those are representing different species. So that's going to be your categorical variable there. So this is showing us, so this is going to be two quantitative, because remember, if we have a scatter plot, it's always going to have two quantitative, but we also have one categorical, which is going to be our species. So yeah, that's just another way you can do it. This allows you to check out the strength, direction, form, and outliers of different data, but if they have, like, if you want to look at different groups, so now you're able to compare these different species instead of just one against itself. So, all right, correlation. So this goes a little bit, this is like a kind of going back to scatter plots a little bit, but the main thing with this is correlation has to do with strength and direction. Correlation is always going to be between -1 and 1. And that's why, and a lot of people ask them because they're like, well, wait, this table over here only has numbers from 0 to 1. But if you see the top, it says absolute value of R. So as a review of what an absolute value is, that's how many units away from 0 it is. So absolute values can't be negative. They're always going to be positive. So, and keep in mind, correlation is unit free. We don't say it's 0.2 something. It's just a correlation of 0.2. R's, that's all your correlation is. So yeah, they don't have to be on the same scale too. That's another thing to keep in mind. Your x and y variables, you can, like in that last one, the petal length could be in centimeters and the height can be in width, or length can be in centimeters, height can be in inches, whatever, and that doesn't matter. It's totally, fine in regards to correlation. You don't have to do that. You don't have to like convert them. So yeah, for positive linear associations, we're going to have, it's going to be between 0 and 1 in that case. And then for negative, it's going to be between 0 and -1. And think of it in the fact too that we're not talking about like a value of -1. We're talking about like it's a correlation of 1, but the negative is showing that it's downward, that it's a negative direction. It doesn't have to do with value. That's why there's no unit attached to it, because we're not talking about values. We're talking about the direction, because correlation is strength and direction. So the actual number you have is your strength. So the 0, 0.1, 0.2, 0.3, whatever that kind of thing is, that's your strength. And then your direction is going to be either the negative or if it's a positive number, that's your direction. So those are the different parts of it. 2 quantitative variables, keep that in mind. Yeah, correlation is, it's not resistant to outliers. It will be affected by outliers. So for example, if you were to have a graph that looked, like this, and it was like, oh, nice, check out that correlation. So let's say I said my correlation was something like -0.9. But then, all of a sudden, we get like an outlier that's like over here. Then my R might turn into like 0.85 or something, because it's going to go down, because whatever line was here is getting now pulled more this way. Not that drastically, but this, outlier is pulling it away. So that's going to change our correlation here. It's the main point. How many? Okay, so how many variables are included in a box plot and what type? Okay, so that's a good question. So on a box plot, those are basically, all those are like from a 5-number summary. Those are technically quantitative variables because they're just numbers. So because you can put anything on a 5-number summary or on a box plot, there's going to be numbers. They're not going to be categorical because you wouldn't put categories on those places. You can't like make a value attached to them. But so yeah, a box plot's just a bunch of different values. I wouldn't necessarily, I guess the values are going to come from a quantitative variable. So like if it's like car speeds, that's a quantitative variable, but then that 5-number summary are just different car speeds. So I guess you could say it's quantitative variables, but it's more so, yeah, no, definitely. It's more so just numbers chilling. But yeah, that's a great question. I'm glad you asked. Okay, cool. Let's keep on trucking. All right. Okay, simple linear regression. A lot of people just kind of breeze over this because they feel like they've seen this before. But make sure you understand the different parts of it. I mean, a lot of people have seen the whole like y equals mx plus b. That's a common thing in like high school algebra, that kind of thing. But keep in mind that when we're in statistics, we're talking about it's the whole like reason it's called simple linear regression is it's one explanatory variable. That's why it's simple, and then the linear part comes from the fact that it's a straight line. So as you can see, we have our y-intercept is our b subscript 0. That's our y-intercept. That's going to be where it hits. And then let me actually draw this out. So if we have a graph here, living life. So here we would have our, this would be our y-intercept. Wow, don't know what I did there. All right, so that's our y-intercept. Our slope would be whatever this is here. So we call that our b subscript 1. It's going to be our slope, our rise over run. And then, oh yeah, and then our y is just going to be whatever point on that we're looking at. That's going to be whatever value, like our predicted y value, our predicted value of y at a given point of x. So let's say this is our x value. That's going to be y hat, our predicted y. So whatever's on that line. So yeah, that's simple linear regression. Just putting a line through some stuff. Okay, residuals. Residuals are something that basically we use to discuss like the difference between what we saw and what we think or should have happened. So our predicted y value, if you remember from the last slide, we get that predicted y value from our simple linear regression line. So on that line, there's a whole bunch of points on it, okay? And these are all of our predicted y values on the line that we get from the simple linear regression. But then when we observe, like whatever we observe, it's not always going to be directly on this line. It's going to be all around it. So dependent on how far away the points around it are, those are going to be our residuals. How far away is from our line to the actual observed values. So I probably made no sense. I was just swinging my pen around, but I will draw it out. So let's say that this is our simple linear regression line, okay? And these are just a bunch of points on the line. Just to, you know, any point on here can be there. And then let's say, actually I should have written it this way. All right, so predicted y value. So I'm using this color. Assume that that's what I meant. Okay, so our predicted y value, it's going to be anything on here, on this regression line, okay? But then we have observed values, okay? So these are going to be all the different values that we actually observe in our observation. It could be right on the line. It's possible. So these are going to be our observed y values, okay? And then we are going to have our residuals, which are going to be between the actual line, the predicted, and then the observed. So this black line I drew in here is our residual. A residual here that's on the line is going to be 0 because it's on the line. Here's another residual, another one. So yeah, it's basically the space from your predicted y value from the from what you predicted should be on your regression equation to your observed value, which is going to be what you actually found. That's all residual is. That picture's creeping me out, so I'm going to clear it. Okay. Let's see. Oh, we're already at reviews. How exciting. All right, so we will do these. See what's going on with these. Okay, so which of the following cannot be answered from a regression equation? So go ahead and read these over. Let me know what you think, and then we'll go over them together. Okay, wait, let me see. Let me hope everyone answered 3, 4, 5, 6, 7, 8. Okay. Going once, going twice. Just kidding. Take your time. We'll start going over it just so we keep on cruising. Okay, so this is asking what cannot be answered. Okay, so we're looking for which one of these or something that if we have a regression equation, we can't use it to answer this. Okay. So for A, it says predict a value of y at a particular value of x. We can do this because if you remember, our regression equation is y hat equals our y-intercept plus our slope times x. So if I give you an x value, if I said that x is equal to 4, and let's say that your slope is equal to 1/2, And then, your y-intercept was 2. I'd be able to find predictive value of y at a particular value of x if I have this regression equation. Because in this case, I would have a regression equation of y hat equals 2 plus 1/2 x. So that I just use this information to make this equation, okay? And stop me if this gets confusing. So let's say you have a regression equation that looks like this. I just made these numbers up, okay? So, and then in this case, if I said that x equals 4, all I would do would be plug in x, 4 for x, so y hat equals 2 plus 1/2 times 4, if I were to say that, and then I would be able to predict our y value, which would end up being 4, actually. But, so you actually can do A, so that's not true, okay? B, estimate the slope between y and x. You can, because that's all that B1 is, so you could do that. So B subscript 1, so that's possible. C, estimate whether it's positive or negative. You can do this just dependent on if your slope is positive or negative. If you had, so in this case, given this equation, is my slope positive or negative for this y hat equals 2 plus 1/2 x? Is my slope going to be positive or negative here? Yes. Good job. All right, perfect. Yep, you guys got it. So this is positive because we see this plus sign. If I had an equation that looked like y hat equals 4 minus 6x, this is going to be a negative slope. So you guys basically answered this question here because we can estimate whether or not it's positive or negative just by looking at this slope. So it's definitely not C. So D is going to be the correct one because we can't estimate whether the association is linear or nonlinear if we only have a regression equation. We don't have the rest of the information, so we can't, number one, we can't make an association in general just because our regression equation is always going to be linear. That's why it's called a simple linear regression. So that's always going to be linear, but we have no clue what the association is going to be without all the other information. So just looking at a simple linear regression equation isn't going to tell you that. So you can't answer D from that information. Does that make sense? I'm just going to draw this person until you guys. All right, cool. Yay. Oh. Yeah, she's having a bad hair day. Okay. All right, cool. Good job, guys. All right. Number 2. All right, a regression between foot length, response variable in centimeters, and height, explanatory variable in inches for 33 students resulted in the following regression equation. Y equals 10.9 plus 0.23x. One student in the sample was 73 inches tall with a foot length of 29 centimeters. What is the predicted foot length for this student? So go ahead and solve this one, and then we'll go over it together. All right, let's go over this one. So, what I like to do when I have when I have questions like this, because in stat you're going to see a lot of word problems, and to me that's like, whoa, like this is not English class. What is going on? So what I like to do is take out all the information that I have to kind of organize on the side of my paper. So in this case, so we want to first write out that we have length is going to be our response variable. And then we're going to have height. That's going to be our explanatory variable. Okay, so those are two things to keep in mind. We have 33 students. Our n is going to equal 33. And then our regression equation is equal to y equals 10.9 plus 0.23x. Okay, so let's look first really fast. Well, okay, one thing is our response variable our x or our y? Yes, good. Good job. Yeah, so our response variable is going to be the y. Our explanatory is going to be then, obviously, our x. Okay, and then from this, we found, so 73 inches tall with a foot length of 29. So 73 is equal to x or y? .73 inches tall. So we're talking about height. So is this going to be, is 73 our x or our y? Good, great job. Yep, so 73 is our x. So then, in this case, our 29 is going to be our 29 centimeters, and then this is 73 inches. Our, yeah, and then our y is going to be 29 there, okay? So, we have all this information. So we're looking for what is the predicted foot length. So, are we looking for x or y? These are like the questions you should ask yourself as you're going through, you know, so what is the predicted foot length? What are we trying to find? Are we trying to find the x or are we trying to find the y? Good. Good job. Yep. We're trying to find y because that's our response variable, which is our length. Okay? So, we don't have y. So what we can do for that is when we're writing our equation, we're going to say y equals, because we don't know what it is yet. Our 10.9 in this equation is a constant. So we're just going to stick that there. Plus 0.23, which is technically our slope. But now we're going to plug in x, because that's the one thing. So they're saying that the student has, and this student has like observed he's 73 inches tall and has a foot length of 29. We're trying to find a predicted foot length. So we know it's observed, but we're trying to figure out if we were to use this equation, what will we predict his foot length being given that he's 73 inches tall? So what would I put in for the x here to solve this equation? So we put our constant, the 10.9, plus the slope, 0.23, and then times what would I plug into here to get the answer? Yep, good job, guys. Yep, so this is definitely, we're going to plug in the 73. Because remember, so 73 inches is talking about our height. So remember, up here, our height is our explanatory variable, which is our x. This was x that we plugged in, okay? So all we would do now is to solve this. So y equals 10.9 plus, and if I solve this out, I'm actually going to get 16.79, And then altogether, it's going to end up being 27.69. It's going to be our answer. That makes sense how I walked through and did that? Cool. All right. Yay. Yup. All right, I found a new cool thing on here. I feel like I already showed you guys this. Oh, look, it's called a spotlight. It's called meow, meow, meow. I thought it was exciting. What does this do? Oh, an arrow. Wait, hold on. That's so cool. I can like point to stuff. Wow, I'm sorry. This is exciting. All right, I just found this. Let's make it stop though. Oh, now I got this thing going. All right, enough of this. Let's X out of this. Okay, cool. Good job, guys. All right, review number 3. In the simple linear regression equation, y equals b subscript 0 plus b subscript 1x, the symbol x represents what in this equation? I like the exclamation point. Good job, everyone. Good job. Yep, you guys are all correct. So good job. The answer is going to be D, our explanatory variable. If we go through the other options, see why they're not right. So estimated or predicted response, remember that's going to be our y hat. So that's not correct. And then estimate intercept is going to be our b subscript 0. So that's not correct. And then our slope is our b subscript 1. So that's not correct. So D is our answer. X is going to be our explanatory variable. Good job. All right. That one kind of checks to see if you're listening on the last one. So good job. All right, 2 more. So the IQR gives a range of the middle what % of the data? Yay! Yes, enthusiasm. I dig it. Good job, guys. So yeah, our answer is most definitely B. So if you remember Boxplots, I told you, they're not going to go away. So remember when we break this up into quartiles, each one of these is going to represent 25%. So, and it makes sense too because here's our median. So down here is going to be 50%, and then up here is going to be 50%. But then also within the box, the interquartile range is going to you have to. That's what I always tell myself, you got to be confident in your answers, and then they're usually right, trust me. But yeah, so then this is going to be 50% of the data because you have the other 25% here, other 25% here. So good job. Yeah, so it can be the same thing. Oops. Okay, yeah. Same thing here. So it's literally the same exact thing. So just like you literally could have just turned your head on my last one, it would be the same thing, So you're gonna have your median here. And then, if it's on a graph like this, here's gonna be your lowest number, and then here's gonna be the highest. So this is gonna be your max. So what about when you have to find the 10% and the 90%? You probably would not utilize a box plot for that, only because the box plot is giving you technically the 5-number summary, so it's giving you your minimum, your maximum, and then your quartiles, which includes your median. So if you're trying to look for like the 10th percentile, is that what you're asking, and the 90th percentile? Like, I would not necessarily use it. Yeah, I wouldn't use a box plot for that one. But to answer your question, Anna, this is always, it's the same exact situation here, just broken up this way. Of course, yep, Q1 and then Q3. Yep, good questions. You guys are thinking. Good job. All right, one more. Okay, so given a 5-number summary of 190, 240, 250, 280, and 300, identify which of the following would be an outlier in this case. Okay, great job. Yep, so remember to find our IQR in general, we're just going to take our Q3 minus Q1. In this case, it would be 280 minus 240 minus, it's going to be 40. And then if we multiply that 40 times 1.5 for the IQR method, then we're going to get 60. So that's showing that anything above 60 in and out is going to be, from the right to the left is going to be an outlier. So the only one that meets that criteria is going to be D390. That's going to be at least 60 out there. So good job. Alrighty. Alright, cool. So good job. You guys did a great job tonight. Definitely have a good grasp on all this. So obviously go ahead if you want to relive this moment. I know I do. Go ahead, watch these back on YouTube. And our next review will be on Sunday. Same content, same PowerPoint. Bring new questions if you want. Okay, cool, yeah. And all right, cool. And then if you haven't given me your email, go ahead and type that in the chat box for me. And that's fine. I like having a squad, every semester. It's fun having our people that come in to hang out, because then I have nothing to look forward to on Thursday nights. Then what am I gonna do Thursday nights if you guys don't come here? Like, this is my life. But yeah, so if you have any questions, go ahead, type them in the chat box. Yeah, this is also true. I need to get into the football thing. but yeah, I'm here if you guys have any other questions. List of those stat symbols. Are you saying like P and sigma and p hat, all that kind of thing? You can honestly Google one. I'm pretty sure I have one in my upcoming reviews when we actually get more into that. But you could Google one. But yeah, like I said, I'm pretty sure I have one one of my upcoming reviews where we have to differentiate more between statistics and population parameters. So, but yeah, I would try Googling it, honestly. You could probably find something there. Of course. I'm glad you guys enjoy it. Good night, everyone who's going to bed. Maybe you're not going to bed, maybe you're just leaving me, but have a good night. Different graphs. So, as in like all the ones from last week and this week? Yeah, so you guys want me to review like if bar graphs are used for categorical or that kind of thing? Is that what you're asking? Okay, yeah. So what you should do first, go ahead, because I talked a lot about them in my last review. So go to my like Thursday or my Sunday review for last week and look at those because I went pretty extensively into them about you know, which ones are for categorical variables, which ones are for quantitative, that kind of thing. And then if you still don't understand after watching that, then we can go ahead back on Sunday, okay? But I feel like you might get most of your questions answered from that review. So. I think you'll do great this semester. You definitely have a good background, so I think you will do a great job. All right, sounds good. Let me know if you need anything. You're very welcome. True. All right, good night.